This is a demonstration of Vali energy management systems applied to gas plants, or in other words, how to save $100,000 in 15 minutes. We, Belsim, are an engineering company based in Belgium with about 30 years of experience in the oil and gas industry, offering solutions and services around our software suite Vali, which is based on data validation and reconciliation technology. We have a presence worldwide, in particular in Europe, Middle East, and North and South America. Our solutions are based on mass and energy balance solutions, deploying full thermodynamic packaging in the upstream and downstream industry, and also power and utilities. Our customer base is covering various industry sectors all over the world. Just to name a few, very recently, prestigious greenfield installations such as Satorp and Yasref in Saudi Arabia, but also globally operating oil and gas companies such as Total, Saudi Aramco, BP, or Air Liquide. Our solutions are based on technology called data validation and reconciliation. In the next couple of minutes, I'm going to show you very briefly the principal concepts of DVR. DVR is a technology based on a mathematical modeling of a process by using a certain set of equations and certain set of variables. Those equations can be, for example, mass balance, energy balance, compound balances, or reactions, for example. Those involve state variables such as mass flow rates, molar flow rates, pressures, temperatures, densities, and so on. All those informations are put in a large mathematical model that represents a process. And the objective of data validation and reconciliation is to match data so that the data is representing as closely as possible the actual process operation. To illustrate this, let me show you this small example of a mass balance model in which you have one inlet streams on the left and two outlet streams on the right. As you can see, the measured flow rates do not balance, so we have 31 mass inlet does not equal 21 plus 10 mass outlet. The reconciliation technology is reconciling these measurements to satisfy the system constraints, which in this case are the mass balance constraint, in order to achieve a set of data which is consistent with respect to this model. Based on this DVR technology, various applications can be built which aim at different objectives and satisfy different customer demands. For example, production accounting, loss management, condition-based maintenance, and so on. In this following example that we are going to show, we are focused more on mass and energy balancing and performance monitoring. Let me show now the business case that we have chosen to illustrate the benefits of Vali energy management solutions. The case that I'm going to show is on a project that we have developed for a customer which is located in the Middle East and is operating a gas plant facility which is mainly producing NGL. The setting of this project was the global objective of the company to reduce its energy intensity index by 10% over a period of 5 years. This objective has been achieved by identifying opportunities of energy savings by implementing a system that is monitoring KPIs such as plant energy indicators, efficiencies of individual equipment or whole groups of equipments, and globally to improve the quality of measurements. Why has the customer chosen Vali as the preferred tool to achieve these objectives? Well, Vali is a tool which is based on a thermodynamic package combined with the statistical techniques to reconcile data in a most rigorous manner. It also allows to estimate and calculate unmeasured variables such as KPIs, and it also allows to detect early poor process performance, which may have a negative impact on the energy use. And operational opportunities may be highlighted in order to save energy consumption. The scope of the of the demonstration that I'm going to show in the next couple of minutes is limited to boiler management, even though the scope of the model itself is much larger than that. So what we are going to show is how to save the order of $100,000 per year in just a few clicks by analyzing and exploiting the information which is available in the most efficient manner. The starting point is always the analysis phase, in which we look at KPIs such as boiler efficiencies in this case. By using information generated by Vali, it is possible to identify energy inefficiencies. So this is what you're going to see. It will also highlight boilers which are the most efficient ones, which should be preferred with respect to the loading. Actions are recommended through the system, which are then implemented by the plant operators to better manage the boiler utilization, which then in the end results in potential savings in terms of fuel consumption. All right, so let us jump into the application where we are going to show how to pinpoint energy saving opportunities in the order of $100,000 per year. The business case that I'm going to use is a boiler load management, where we are going to see how to model boilers inside Vali and how to extract information produced by Vali, which is available in an SQL database, to identify saving potentials. To get started, let me quickly introduce the concepts of modeling parts of a process. So here in this application, we have modeled the whole steam system, fuel and power system. So inside the steam system, we have the boilers. So here we have a boiler section of this gas plant in which there are 6 boilers available, not all of them operating at the same time. So we see, for example, boiler 5 is being put off, so it's not producing at this for this particular run. Each boiler is modeled in a similar manner. So you have the reactor, which is taking fuel gas, air, producing fumes, which are transferring heat to the boiler feed water that is producing steam. It's important to note that this model is based on a fully thermodynamic process representation, meaning that all the energy provided to the system equals the energy that is coming out in one way or another. So in particular, the main inlets are the fuel as material streams, the air and the boiler feed water. As material streams leaving the system, we have the steam and the blowdown. And then we also have heat losses as part of the reactor and the power provided to the pump. So each individual equipment, like for example this reactor, again is based on the full thermodynamic mass and energy balance based modeling, where we have in this particular case model this reactor based on an atomic and energy balance basis. So it means all the atoms entering the reactor equal the atoms leaving the reactor, while still conserving the possibility that there is some heat produced which cannot be recovered elsewhere. So these are considered to be heat losses. Other important equipments are these heat exchangers here, which are key for the identification of the performance of the equipments. So those transfer heat released through the combustion here to the boiler feed water to produce high pressure steam. So here each of these heat exchangers have multiple parameters, for example the heat load, the heat exchanger area and heat transfer coefficients. So those parameters are dynamically recalculated with each run and continuously available to you to continue the performance of these individual equipments. The KPIs of this boiler, they are being calculated also with each run. So for example, you have the boiler efficiency based on the fuel heating value, which represent the amount of heat transferred from the flue gas leaving the reactor and transferred to the boiler feed water, which becomes the steam. So this amount of heat that is being recovered in the steam is being defined as the boiler efficiency based on the heating value. The other efficiencies also like excess air, like steam to fuel ratios, for example. We will come later back to this concept. So to analyze the performance of these boilers, so we've seen that there are altogether 6 boilers in this gas plant. What we can do and what someone can do who has access to historic data is to plot the efficiencies of these boilers. Efficiencies, for example, being defined as efficiency based on the heating value of the fuel, so the amount of heat transferred to the steam flow. So here we see for this selected period of 30 days, there are at any given moment 3 or 4 boilers operating. For example, at the beginning of the period we have boiler 1, boiler 5 and boiler 6. The others are not operating. Then after some days boiler 4 is being is operated as well, and so on. What we also observe is that these efficiencies being calculated on raw measurement data, they are not at all consistent. So in particular, you will see that the efficiencies are above 100%, which is clearly not possible. So let us analyze now this process a little bit further in order to answer the question how to manage these boilers, or in other words, how to load the boilers in the most efficient manner to save energy as much as possible. As first step, we reproduce this trend by focusing on 2 selected boilers. So let us duplicate first this trend and pick only boiler 1 and 5. So the others, for the sake of this analysis, are being ignored. So we see here again, like before, that these efficiencies are above 100%, so clearly not realistic values and clearly not something which help us to identify which of the 2 is better. Both are in the order of 105% efficiency. So the natural question that arises is, so how to assess the actual performance of these boilers and to decide which one is better and which is more efficient. In order to do that, we can use reconciled data produced by Vali. So in order to do that, we have tags in the model which are calculating the efficiencies based on reconciled instead of raw data. Still, efficiency being defined as the efficiency using the heating values of the fuel. So those are different tags here that we are going to show, which give different values, obviously. So we see here that if we change a little bit the scale of the axis from 80 to 90 and the steps of the order of 2, we have a trend representing the efficiency of the same boilers for the same period, but with a different with efficiency values which are much more realistic, so in the order of 83-84% efficiency, which is in line with the performance curves of these boilers. So here we see that boiler 5 is clearly more efficient than boiler 1, so the efficiency is higher by about 1 percentage point. So if we had the choice between those 2 boilers, we would clearly prefer boiler 5 over boiler 1. So what does this mean in terms of economics? If we digest this observation, we see that if we have the choice, we would prefer boiler 5. So let us look now at the economics and the impact that this knowledge has on the operation of the plant. So here we have a different KPI, which is saying essentially the same thing than what we have seen before. It's not the efficiency based on the heating value, but the steam to fuel ratio, which is another KPI representing the performance of a boiler. It says essentially the same, that boiler 5 is more efficient than boiler 1 by about 0.5. So this 0.5, what does it mean? It means that for the same amount of fuel, we produce 0.5 units of steam more when using boiler 5 compared to boiler 1. So for example, if we take the scenario of steam production of 100 mph steam, this would consume us 5.88 mph of fuel when using boiler 1, while it would only consume 5.71 mph of fuel when using boiler 5. What does this mean? Because these numbers are rather abstract in terms of actual economics. We can continue the analysis by putting certain assumptions on the price and on the heating values of the fuel. So if we assume this steam production of 100 pph of steam that, for example, could appear when we have a higher steam demand from the process side, or, for example, we may want to switch load from boiler 1 to boiler 5. If we assume a fuel density of 21 SCAF per pound and a heating value of 1200 BTU per SCAF and a fuel price of $3 per MMBTU, we arrive at the following conclusion. So this savings in terms of fuel consumption represent 0.17 mph for this 100,000 pounds per hour, which is the difference of these two fuel consumptions here. Multiplied by the fuel density, we arrive at almost 28,000 MSCF per year. Multiplied by the heating value, we arrive at about 33,500 MMBTU per year of fuel that can be saved by choosing boiler 5 over boiler 1. And using the fuel price that we have assumed of $3, we arrive at about $100,000 savings per year, which can be achieved by just exploiting the fact that we see this difference in boiler efficiencies. And I recall that this fact cannot be exploited by just looking at the initial efficiency curves that we have seen here by using raw measurement data. So this means exploiting this fact that we have reconciled data and analyzing these results in a smart way. There are savings potentials for the fuel in the order of several $100,000, because this is just one particular case which we have identified these kind of potentials. So this concludes the results and findings obtained in Vali energy management systems applied to a gas plant model. If you want to know more about our services and solutions, please visit our website www.belsim.com.